Hi, my name is John and welcome to another edition of Statistics Quest. Today I'm going to talk to you about Bayes' theorem as it relates to COVID testing. So if we go over here, we have a couple words to define. One is sensitivity. That's the probability of getting a positive result if indeed you are infected. And specificity is the probability of getting a negative result if you are not infected. So in the first case, it's getting a positive where you want to get a positive because you're infected, right? You want the test to be correct. Specificity is just kind of the reverse of that. It's the probability of getting a negative if indeed you are not infected. And the better the test, the closer these numbers are to 100%, right? So we hope to have a test where we find the positives accurately and we find the negatives accurately. Of course, no test is perfect. And in this case, we're going to assume that both the sensitivity and specificity are 98%. Those are reasonable numbers. It's really hard to pin down exactly what it is, but we'll assume that to be the case here for the example that we're going to go over. So I actually just found this on the internet. This was from London about a year ago, February 2021, and they had determined that about 1% of its citizens had COVID at that time. Okay, so we're going to use these assumptions. 1% of the population has COVID with 98% sensitivity and specificity. And again, these numbers and terms, when you sensitivity, specificity, I mean, it might be a little bit intimidating, but when you break down the numbers, it's actually a lot of 8th grade math, quite frankly. Piecing together the math is, somewhat of a diligent process, so we want to be careful. It's very easy to get things mixed up when you have a lot of symbols and numbers floating around. So, but let's attack this, and we'll look at each piece of Bayes' theorem, and we'll see that it's really not that difficult if we reason through it. Okay, Bayes' theorem is written symbolically as the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. Okay, so let's say we have a question where, somebody's in London, but I mean, they don't need to be in London, but with the assumptions given, right, 1% and then the 98%, and they test positive. We want to find the probability that they have COVID, right? Of course, they test positive. That doesn't mean they necessarily have COVID. We're going to see the probability that, and we can determine that under these assumptions. Well, it's very important if you're going to use Bayes' theorem to write down symbolically the meaning of these letters, okay? That's kind of sometimes half the battle. So if you write this down in front of you, and any of you who have taken a statistics course, in particular with something with Bayes' theorem, you know the importance of just kind of following the, what the A's and B's represent. Sometimes it's just a matter of plugging in numbers, and it's, a lot of it can be pretty simple, but you need this... You need this to have, and certainly you could have it in your head, and I used to try to do that, and it's not such a good idea. So let's write it down. Okay, so we're going to write down A is the person has COVID, B is the person tests positive. So this symbol, probability of A given B, really means what's the probability that the person has COVID given that they test positive. And that's exactly what we're asking, isn't it, from the original question. So this makes sense for what we've written for A and B. Okay, we want to use the right side of Bayes' theorem and plug in numbers. Some of it's easy, some of it is, well, we'll see in a second. We kind of have to think through it logically, and we're going to break it down, okay? The numerator is actually pretty easy. The numerator has the probability of A. I'm going to start over here because this is probably the easier part because it's just the probability of A. That's easy. That's just 1%, okay? Because that was from our original assumption. The other part of the numerator from Bayes' theorem is the probability of B given A. What does that mean? That's the probability that you test positive given that you have COVID. Oh, we already went over that. That's the sensitivity, the probability of testing positive given that you have COVID. If you have COVID, you're going to get a positive result 98% of the time, and so that's just 0.98. So the numerator is pretty easy. The denominator, that's the probability of B, that's the probability of testing positive. This is not so easy, and in fact, it's not given to us directly, so we're going to have to find it kind of, you might say indirectly, or another way of phrasing that, we're going to have to break it into pieces, so to speak. And here's how we do that. Well, we might test positive by either having COVID or not having COVID, right? For example, if you go to the doctor and you test positive, you know that you've tested positive, but you don't know whether you have COVID or not. I mean, you think you have COVID because you tested positive, but you might not. You might have COVID or you might not have COVID. So there's actually 4 pieces to this. You might have COVID and tested positive, or you might not have COVID and tested positive. We do know you tested positive, but we're not sure about having COVID or not having COVID at this point. And that's what we're going to attach a probability to. Okay, so there's really 4 parts. Having COVID, testing positive, not having COVID, testing positive. Notice you have the word and here. And actually translates to multiplying in statistics, at least in most contexts, and it does here. So we're going to multiply this by this. You have the word or here. That translates to addition. We're going to add that to multiplying this by this, right? Okay, so we're just going to take the components. Okay, so what having COVID and testing positive, well, this is the probability of testing positive given that you have COVID times the probability of having COVID. So forget this given part for a second. It gets into dependence and independence, and I'm not going to go there for this session. You can always ask a question in the comment. But basically, we're going to keep this simple. Having COVID and testing positive is multiplying B times A, and that's what this does here. Not having COVID and testing positive is multiplying B, which is testing positive, times not A, which is not having COVID. 4 parts. Okay, what's the probability of A? Well, it doesn't matter which way we do this, but let's look at the probability of A, which is having COVID. I'm going to start here just because I think that's the easier part. We earlier said that's 0.01. What's the probability of B given A? We also earlier said that's 0.98. And in fact, you'll notice this 0.98 times 0.01 is actually, at least this part of the denominator, is the same as the numerator. And that's kind of a check that is always going to result in a Bayes' theorem problem of this nature. Now, you have many different types of natures of Bayes' problems, so I don't want you to expect that's always going to be the case, but in this case, we can kind of double check this. Okay. This part's a little bit different, but let's just reason through it and we'll see it's not so difficult. In fact, let's start with this part, the probability of not A. That's actually pretty easy. Well, if the probability of A is 0.01, then the probability of not A is 1 minus 0.01, which is 0.99. That's this part. What's the probability of B given not A? Well, again, let's go back symbolically. That's the probability of testing positive given that you don't have COVID. Well, the specificity we said earlier was the probability of getting a negative given that you don't have COVID is 98%. So then the probability of getting a positive given that you don't have COVID must be 2%, right? Because if you're getting a negative 98% of the time, you are getting a positive, you're testing positive 2% of the time. So it's just 1 minus 0.98, that's 0.02. So here are the 4 parts to the denominator. The rest is easy. Here's the numerator of Bayes' theorem. Here's the denominator we just calculated. That works out to a mere 0.33, or about 33%. So what is that saying? That is really saying under these assumptions, which are pretty reasonable, there's just a 33% chance that the person did have COVID. Now, what if you say, well, okay, I want to get a second opinion? It's not a bad idea, especially under these assumptions. Actually, it works out pretty easy, because remember how our earlier assumption was 1% had COVID? Well, now you've kind of updated your probability to 33% because you tested positive the first time. So now if you go into a second doctor, or you just take a second test, it doesn't matter if it's a second doctor, now instead of the 0.01 that we started with, which appears here and here, we're going to use 0.33. Actually, everything else will stay the same. And I don't show the calculation, but if we substitute a 0.33 here and here, and we calculate it, we get, voila, 0.96. What a difference a second test makes. So again, that's assuming that you get a positive on the second test, right? If you get a negative on the second test, then everything goes out the window here. But as positive on the second test, under these assumptions, says that you have a 96% chance of having COVID with a second positive test. So kind of interesting. We get much closer to 100%. And, there's the old expression, get a second opinion. That holds true in a lot of areas of life, right? Whether it's COVID or, cancer, broken leg, whatever. Now, today, compared to, say, 50, 60, 70 years ago, we have better technology. So, that 98% that we assume for sensitivity and specificity, that might be closer to 100%. But there are actually, it's an interesting, there's something called a base rate paradox in Bayes' theorem, and it actually has to do with the underlying assumptions. I'm not going to get into that, but again, this is a very interesting result. It's kind of counterintuitive, because you're thinking, boy, not many people have COVID, and we have pretty good testing, and you said, wow, how did we get 33%? Well, we got 33% because essentially Bayes' theorem says so. And again, we do get misleading results because of that base rate fallacy that I mentioned earlier. So again, a second opinion here might be warranted. But so again, I'm not advocating anything in this fashion. Whether you should get a second opinion or not, that's all up to you. But I found it interesting, and it's a good application of Bayes' theorem. So I wanted to go over that. Certainly it's topical. So anyway, I hope you enjoyed this episode of Statistics Quest. If you have any questions, feel free to leave them in the comments section, and I'll make a point to get back to you. In the meantime, like and or subscribe if you haven't, and we'll see you next time on Statistics Quest. Thank you.